Thanks for the introduction, and thanks all of you for being here. So what I'm going to talk about, and this is about AI, and very recently AI has got very bad press, a lot of cases where AI was not performing very well. And today I'm going to talk about a topic that we are actually already studying for more than 10 years, about machine learning fairness, and hopefully also give some solutions there. So it all started out with the promise of artificial intelligence. Human decision makers are susceptible to prejudice and bias. We all have our own gender, racial stereotypes, even if it's unconscious. And because of that, the decisions we take are automatically colored, and we maybe not take the right decisions in all cases. However, if you look at artificial intelligence, machine learning, that's based on statistics, on lots of data, mean standard deviations, whatever. So the hope was that artificial intelligence could make decisions that were free of bias, and because it's no longer based on gut feeling, but facts and statistics. However, it quickly turned out that artificial intelligence, and because it's based on data generated by people, also picks up patterns that may be missed by humans, but artificial intelligence also picks up some of our bad things that are present in the data. A very good example is Tai, the chatbot, and this was in 2016. This was launched by Microsoft. Via Twitter, you could interact with Tai, the chatbot. And in the beginning, Tai was very nice and was giving tweets like reacting to people. Can I just say that I'm stoked to meet you? Humans are super cool, a very positive message. But very quickly, this changed. The tone of Tai, the chatbot, and Tai became Tai, the racist chatbot. It was not programmed to be like that, of course. It was put out in the open by Microsoft. They don't want to have this kind of bad press. But by interacting with people, after a while, within 24 hours, actually, it became racist. For instance, someone is commenting, you're a stupid machine, and then Tai was answering, well, I learned from the best. If you don't understand that, let me spell it out for you, adding insult to injury. I learned from you and you're dumb too. And like even explaining the insult, which is even more insulting. However, you could even say this is maybe a bit jokingly, it's funny. But then, do you support genocide? Apparently, Tai does. And then this one tops it all. Bush did 9/11, so some conspiracy. Hitler would have done a better job, so maybe some negationism. Then the monkey we have now, racism. Obama was in the White House at that time. Donald Trump is the only hope we have. And so very quickly, Tai became racist. So how did it come? So partly you can find a lot of interactions with Tai where actually the racist comments of Tai come from people that are saying, repeat after me, and then they say something racist, and Tai is a very nice machine, repeats after them. But also even not interacting in that way with Tai, Tai basically picked up this kind of patterns, and people were really teasing it out, and it was giving this kind of reactions. Of course, Tai was trained on a lot of data that was available online, also discussion groups that were not always well moderated and that contained this type of content, and because of that, basically it slipped off. So AI may unintentionally pick up and amplify bias from observations, leading to unintended effects. I don't think Microsoft intended this type of behavior from Tai. And this can be particularly problematic when the models are very complex. Deep learning is really a thing nowadays. Models are so complex we don't really understand on what basis the machine is taking a decision. If you would write down the mathematical formula, of course, it's like kind of transparent. We can see the input goes in, an output goes out, comes out, but we do not really understand how it interacts. If you look at the formula, you would need a telephone book-sized book just to write down the mathematical formula to take the decision. And so it cannot always be explained. Here is another example. Here we can explain somewhat. And this was in a shop in the United States, where they were selling Barbies, the same Barbie, a black version and a white version. The white version was sold for $5.93, the black one for $3. Clearly not sending the right message. that the white Barbie was more valuable than the black Barbie. Why was this? This was because an automatic inventory system was being used here, and the automatic inventory system, this was probably in a neighborhood that was predominantly white, so mainly the white Barbie was sold there, and because of that the price was higher. It all makes sense from that perspective, but the machine does not know about the stereotypes, does not know about the sensitivities in the country. So why is it important for AI to be fair? Do we just want to be politically correct? No. It's, of course, we prefer to be good people and to be ethical, but also there are some legal restrictions and also reputation damage. At TAI, the chatbot, this was a very good example of a lot of reputation damage done to Microsoft. But besides that, there are also discrimination laws that will not allow the use of certain attributes when making decisions, not even indirectly. And so directly, that's clear. You cannot use gender of a person in order to hire or not hire the person, but also indirectly. If you look, for instance, at the hobbies, and hobbies are correlated with the gender of a person, you're not allowed to use the hobbies of the person unless you have a very good reason to do that. If the hobby is directly related to the job you're offering, then you can use that. Otherwise, it's not allowed to do that. What we see here is already from 2011 at the European Court of Justice, a decision that was taken in the case of insurance, where they actually ruled that the gender of the insured individual, that you cannot take that into account in insurance contracts because that constitutes discrimination. And this caused insurance companies to no longer be able to use gender. Different countries were allowed to have exceptions to that rule. In Belgium, they didn't. I do not know about Estonia. But for instance, if you go for car insurance, as a direct result from this ruling, car insurance became more expensive for women and slightly less expensive for males, because gender is correlated with the amount of accidents that people make. But according to the ruling, it's not gender that determines whether you're a more risky driver. It's a correlation. For decision making, for prediction, correlation is fine for prediction, but decisions requires causality. What do I mean by this? For the insurance company, it would be perfectly acceptable to use gender in order to assess their total exposure to risk. And to use that in their models, but not for taking individual decisions for people. So if we're building models and we're deriving models automatically from data, AI will pick up, machine learning will pick up this correlation between gender and making accidents, but it's actually legally not allowed to do so. Another example, another reason is about distrust in automatic decision-making. It's very important that people trust the automatic decision-making. Siri in the Netherlands is a very good example where that completely went wrong. You can see a report from Algorithm Watch. Algorithm Watch is a non-governmental organization looking at algorithmic fairness, and so they're evaluating lots of automatic decision procedures, and then when they're publishing reports about that, if they think something unfair happened. In Siri, that was absolutely the case. So what is Siri? Siri stands for Systeem voor risico-indicatie, System for Risk Indication. So this was basically some kind of scoring system that they used in order to find out which people in the Netherlands were more likely to be fraudsters. And for that, they collected data from many different governmental organizations. You see them there on the left, the tax office, municipalities, immigration authorities, also some social security. And if you would commit fraud in one of those offices, and that would basically be gathered, all this data would be collected, be anonymized, a risk model was built. Then, based on the risk model, people were classified as being suspicious or not suspicious. And after that, if they were deemed to be suspicious, they would be, then the data was de-anonymized again, and then there was decryption. And that was sent back to the governmental institutes. And then they would be checked much more thoroughly. being checked much more thoroughly. This also meant, if you looked at Social Security, that benefits payments would be blocked until they were cleared. And even if there were very minor misdemeanors that they did, like they underreported or overreported by a small amount, this could have drastic results. And the results were really dramatic for some people, like losing the benefit money. Some of them ended up in poverty, lost their children. Some people even committed suicide because of that. And actually, it turned out that this system, that Dutch state was convicted because Syria was in violation with the EU Human Rights Treaty. One of the reasons was, or the main reason was disproportionality. And by disproportionality, we mean that the means are just too extreme for the goal they try to reach. Fraud detection is, of course, a fair goal. We can do fraud detection, but doing it on such a large scale was being considered to be disproportionate, and considering people to be fraudsters, or withholding benefit payments, was actually being considered as being a disproportional measure in that case. And also in the conviction, it was mentioned that there is a tangible risk of discrimination and stigmatization of citizens that are from so-called difficult neighborhoods. And difficult neighborhoods, and these are neighborhoods which are typically correlated with lots of people with migration backgrounds living there. So even though the system was not directly trained to discriminate, there was some indirect discrimination, and people from those neighborhoods were more often targeted. So even though the main ground of the conviction was the absence of proportionality, the lack of transparency why a decision is taken, and potential biases were also explicitly mentioned in the court ruling. So then, also at the EU level nowadays, and so a lot of those cases were because of discrimination legislation, and that people could show that they were discriminated against by the algorithm. And then people get convicted. Nowadays, at the EU level, they're also working on the so-called AI Act, which likely to be passed into law in 2023, 2024. I don't know exactly. I was told by people with legal background that 2023 is probably a little bit too optimistic. And this AI Act divides AI applications into 4 categories. First category is unacceptable risks. Those are forbidden, like, for instance, social scoring, the way it exists, for instance, in China. Large-scale biometrical identifications. These are considered applications, AI applications, that the EU says, okay, this is something that we do not want, unless in some very specific cases. For instance, you can imagine a large-scale biometrical identification using cameras to find missing children, and this would be allowed, but to do it on a large scale in less proportional cases would not be allowed. Then high risks, these are the interesting applications, I would say, from a research perspective. They are regulated, which means that we need to be transparent. Why are decisions being taken? So if you use a black box model, we need some kind of way of explaining why a decision has been taken. Accountable, it needs to be clear who is responsible for a decision. There needs to be human in the loop. There needs to be risk management. By risk management, I mean, if a wrong decision is taken, there should be a way for people to react and to get the decisions turned around. And these are in specific areas, and these areas are connected to applications that have a true and real impact on people's lives. For instance, employment. If you cannot get a job because of your ethnicity, age, gender, this is problematic, and if that's algorithmically reinforced. Education, law enforcement, insurance is also another application area. Next to that, a third category, of course, if you have unacceptable risk and high risk, we also have limited and minimal risk. So these are the 2 last categories. I lumped them together because basically, more or less, they have the same kind of activities or the same kind of measures that we need to take. If you make an application that falls into the limited and minimal risk category, it means that you mainly have transparency obligations and self-regulation. Originally, chatbots were there, and then what does it mean, transparency? It means that if you're interacting with a chatbot, it should be clear for you that you're interacting with a chatbot and not with a human. Other examples of things of minimal risk, like games, spam filters. So there, you do not need to be transparent or have this risk management strategies. Then there are a lot of ethical guidelines for trustworthy artificial intelligence. And so there has been a working group, the high-level expert group on artificial intelligence, that made some guidelines. And basically what I want to do in my lecture is to go a little bit deeper on that and see how we can basically, what they exactly mean and how we can meet this or implement these guidelines. So there are a lot of guidelines, human agency and oversight. There always needs to be a human in the loop. The machine should not take life-altering decisions without any human involvement. Technical robustness and safety. If we employ an algorithm, it should be accurate. We should not employ something that is like a coin toss. Data privacy, transparency, and the most important one for this talk, diversity, non-discrimination, and fairness. So it's a quite interesting and readable document if you're interested in it. It contains some guidelines for responsible AI. And for instance, some of the questions, it organized as a list of questions that you can use as a checklist for your application. Did you establish a strategy or a set of procedures to avoid creating or reinforcing unfair bias in AI systems? So for instance, in the Siri system in the Netherlands, there are some biases towards people from minority groups. Does your system include a strategy to avoid that this kind of prejudice is reinforced in the decision procedure? Did you consider diversity and representativeness of end users in the data? That is another well-known problem. If people are underrepresented in the data, algorithms will perform worse on those groups. A well-known example of that is facial recognition software, and then predicting the gender of a person, for instance. There it turns out that those softwares initially were much better to predict the gender of white people than for black people or just non-white people in general. The reason being that white people were overrepresented in these data sets, which are most often scraped from the internet, and black people are underrepresented. So this is an important question if you're doing this checklist, like you're creating an AI application. Is my data set diverse enough? Do you ensure a mechanism that allows for flagging issues related to bias, discrimination, poor performance of the AI system? And so we also need to have some kind of KPIs, let's say, and key performance indicators that we can compute on our data, and a flag can be raised if that has been violated. Also, is your definition of fairness commonly used and implemented in any phase of the process of setting up the AI system? So we need to have a definition of fairness that is commonly used. Do you consider some other definitions? Did you do a quantitative analysis? And have you mechanisms to ensure fairness in your AI system? So in my talk, I will also go over different types of fairness definitions, and I will also point out some inconsistencies between those measures. Voila. So this was mainly the motivation. Why does fairness matter? And because we do not want people to distrust AI, because then we will not be able to use it. We do not want to do illegal actions, because there is a lot of legislation already, the human rights legislation when it comes to discrimination, and now the AI Act, which is coming our way and will be ensuring that we have a lot of transparency, or that we need to be transparent about our solutions. So I will start by giving 3 recent examples of bias in automated decision making, pointing out 3 different ways or 3 different reasons why algorithms can discriminate or of problematic situations. Then we will go to fairness measures. So how can we measure whether something is fair or not? I will explain the most commonly used fairness measures, so already addressing this issue, and did you use a fairness measure that is commonly accepted? But we will also point out some inconsistencies between the fairness measures. And this is maybe, from an application point of view, very bad news. And we will show that for some of the fairness measures, it's impossible to satisfy all of them at the same time, which basically means if you look from this side to the problem, it can be fair. You look from the other side to the problem, it can be unfair. And then basically you're always vulnerable when building applications. And I will give some recent research about that. I will also go into, but this will probably be for the, not for today, talk about fairness audits. And so if there is a system in place, how can we audit the system? I have a very interesting paper of the American Tax Administration, the IRS, for which it has been studied whether they were discriminating based on ethnicity. It has a lot of interesting viewpoints, and it also shows you like how complicated this issue of fairness is. And then we will also talk about fairness interventions. Can we make algorithms that are fair by design, given the different fairness measures that we have, such that they will pass the fairness audits? But that's probably also for Wednesday and the outlook. So before I continue, are there any remarks or questions already? So I fully support Jaak's statement that we can be interactive. It will be a long day, and if we only will be listening, it will be even longer.
For recording purposes, we should use a microphone. So I don't have eyes at my back, but.
Thank you. As far as I understand, implementing fairness in machine learning models kind of makes the models worse. You kind of inhibit the predictability in the sense that you make it more fair, so to say. So my question is, how should we balance the fairness between, let's say, the model builders who want to, let's say, make very good models that predict reality well versus, let's say, implementing this so-called fairness mechanism so that we don't accidentally misclassify or create situations that don't align with our values. So if we, let's say, implement fairness, we inhibit the model creators. So how would you say this balance? How should you balance this dilemma?
Yeah, this is an excellent question, and it's actually one of the central questions, I would say, in fair machine learning. This is will also be part of the talk. And like this has to do with the fairness accuracy trade-off that we often talk about. If we want to become more fair, we'll become less accurate. There is a multifaceted answer to that. The first thing is, if you look at, for instance, cost-sensitive learning, when we classify things, not all mistakes have the same gravity. For instance, if you have a spam detection system and you misclassify a spam email as being non-spam, that is considered a much less bad outcome than a non-spam mail that is being labeled as a spam mail, right? And so usually you have this kind of trade-off that one type of error is worse than another type of error. So here I think it's also a similar situation. We have some types of errors that are worse than other types of errors because of legislation, because of sensitivities, which make that the most accurate model is not necessarily the best model. With spam prediction as well, and so the most accurate model is not necessarily the best model because we have this cost. So that is one part of the answer. Another part of the answer is that in many situations, and in the example we also see that, the fact that your algorithm is discriminating or is biased is often because there is bias in the data, which is cultural and which cannot be justified by certain facts. Suppose you want to train an algorithm to classify CVs. This person I should invite to have a talk with and maybe hire. This person, this CV, I can already discard from the beginning. If that system is trained on historical data, in which, for instance, females were less likely to be invited for job interviews for IT jobs. Then, if you measure accuracy with respect to your original data set, your more accurate algorithm will mimic this historical situation better, and actually you're more interested in an algorithm, and that will be non-discriminatory and will probably be more accurate in the real world. It's like the data is already tainted, so being more accurate on your training data is not necessarily being more accurate in the real world. It's like a little bit also like transfer learning has similar kind of flavor there. But we will come back to that later on as well, but very good question and maybe a good point to already talk about it a little bit. All right.
I have a small remark question. So some 20 years ago in the UK, there were car insurance companies who serviced only women. So by the regulation of the EU, that would not be even allowed, that you pre-segment your customers.
Well, I'm not a legal specialist, but I think it would not be allowed. No. Probably it is allowed to target certain groups and to advertise, but to disallow certain groups to not enter, or to disallow groups to enter your insurance scheme is probably not allowed.
And another question is to the term fair. In many areas, the fair now refers to data sets, findable, accessible, interoperable, reusable, and everything that comes with that. In this machine learning AI field, a lot of data is private and not reusable by the others. So maybe you can keep that in mind later to say how do you ensure that there are data sets that are fair in that sense that people can use it and reuse it, and so maybe you have some remark immediately on that fair.
Well, I think the use of the word fair in that context, that's like from the EU type of when you apply for projects, that your data or data management principles, that it needs to be fair, like I said, findable, accessible, and INR, whatever. And fair here is more like trustworthy, and the AI system itself needs to be trustworthy. But I agree in the context of transparency, it's probably a good idea, or it's probably necessary that some of the training data on which algorithms have been trained is indeed publicly available. Yeah, if we see like nowadays all the things about ChatGPT and not knowing on which data it has been trained, this can be problematic with respect to transparency.
I understood from your examples and so on that you were mainly talking about the AI being legally compliant. That's what it came down to. For me, the word fairness or fair might actually involve a lot more. Is that somehow an issue which is relevant? Say, for example, if we take, staff selection, as long as there's no discrimination, it's legally compliant. But is it fair? Wouldn't we say like a fair staff selection selects those people which are most able to do the job, which may not be the same as not being just being not discriminatory?
Yes, you're absolutely right. I talk a lot about fairness. Usually when writing papers, we try to look more or to talk more about bias and the absence of bias. With bias, we mean that there are certain tendencies in the data that are there because of some processes were introduced and we do not want the algorithm to take it over. It's an ethical principle. It's also philosophical. It's not the same for everyone what it means to be fair. So you're completely you're completely right there. And there are different ways, and people will also not agree on what is fair and what is not fair. This will also be a huge part of the presentation as well. If you talk about we should hire people that are more capable of doing the job and not necessarily look at gender or age or ethnicity of a person, then you're more looking into things like equal odds or equal opportunity type of measures. If you're saying, okay, we should guarantee there should be some kind of maybe even positive discrimination because we want to guarantee this equity, then we're looking more at measures like demographic parity. And then a lot will actually be about, well, it's not even legally distinguished which notion of fairness we should take or which perspective we should take. It's like a menu and you can pick different measures there. All right, but let's continue with the 3 examples, which will hopefully also illustrate cases where it's not like all kind of gray, but where it's also clear and that there's something is happening that needs to be remedied. The first example is that of racial bias that was found in a major healthcare risk algorithm. And what is it about? This was October 2019. It's a system that was used for more than 200 million people already in the United States. And the goal of the system, of the algorithm, was to predict which patients would need extra medical care in future, so that for those patients already resources could be allocated, and also maybe some actions could be taken to keep them healthy for a longer time. And so identify which patients would benefit from high-risk care management. So if you can early see some warning signs, you can keep people healthy for a longer period, and for the insurance company, they will also cost less. However, it turned out that this algorithm was heavily favored towards white patients over black patients, even though race was not a variable in the algorithm. But does it mean that it was highly favored? And so for a white person, it would more quickly say they are in high need, and so much more quickly this high-risk care management would be allocated for those people than for black patients. So what happens when training the algorithm, and we do like we always do, we gather data. So they take files from the same patients some year apart, I'd say 2012, 2017, 5 years apart. The 2012 data is used to get the characteristics, the features of the patient in 2012. And basically, we want to predict for that patient if he or she will be healthy in 2017. So in 2017, we get the health of the patient. We do this for many patients, building a data set in this way, like age, length, weight, blood pressure, but there were like hundreds of characteristics in there, also some time series and temporal, like how does it evolve, and then the health in year Y plus 5, healthy, unhealthy. However, and then the algorithm needs to connect the characteristics of year Y to the health in year Y plus 5, and then hopefully we can use that in order to predict for a patient if he or she will stay healthy in the next 5 years. However, a big issue there, as you can already imagine, and this is very often the case when we do machine learning, is, okay, how do we decide about the label? What is healthy, what is unhealthy? If someone has an operation within these 5 years, but is doing fine, is this person healthy or not healthy? Or if he or she did not get an operation, but has high blood pressure and has a high risk of cardiac arrest, is this a healthy person or not? So the researchers used health costs in year Y plus 5 as a proxy for health. So if you spend more money on a doctor, you're probably less healthy than another person. So this was used as a proxy. So basically, looking at it with a causal diagram, we have a patient's record. We want to predict the future healthcare needs. For this, we use as a proxy the future healthcare costs of the patient, because our reasoning is that the health condition of the patient is reflected in the patient's record, because otherwise it wouldn't make sense to use the health record in order to make a prediction. And also the health condition is related to the future health interventions, which is then connected to the future healthcare costs. So this is the reasoning, and this looks quite sound and reasonable. However, what turns out is that the future health interventions and the future healthcare costs, that they were connected to ethnicity. Based on the ethnicity of a person, it would be more or less likely that he or she had certain interventions, and this would affect the healthcare cost. For instance, black people on average were poorer, so they were less likely to choose for more expensive interventions and hence have a lower healthcare cost. And it also turned out that the ethnicity of a person was reflected in the patient's record. As you can imagine, if you look at where a person lives, environmental conditions, family conditions, what did they study, and so on, and that it's not too hard to make predictions about the ethnicity of a person, or at least an educated guess. And so basically the algorithm picked up the fact that black people spent less on healthcare than white people in this data set, and from the patient record, even though ethnicity was not a variable, this was then reflected in the future healthcare needs. So what goes wrong here? The labeling, and there is a label bias in this case, because the label does not correctly reflect what we want to predict. That's one thing. Another thing is that if we look at the algorithm takes decisions based on the patient's record. Those decisions are correlated with the ethnicity of a person, and so the algorithm's decisions were probably insufficiently transparent, so it was not clear from inspecting the decisions that were made, and that there some bias has actually creeped in this model. And just to give an idea of the magnitude of the problem, and so if you look at all the patients that are classified as being very high risk, the black individuals had 26.3% more chronic illnesses than the white ones, and so the algorithm was less likely to assign this high-risk label to black patients than to white patients, and would actually miss out a lot of severe cases. So when doing this study, the authors that did this study, it was Obermeyer and other people, they actually went into the health files and tried to make a more reliable label based on research in medical research in order to assess the health condition of a patient, and in that way they could actually make this assessment. Then some remarks on the study by the authors, and I agree to a large extent to that. And the point of the study was not to discourage the use of AI, because these problems are simply too complex. We cannot manage millions of healthcare records by just using SQL and writing our queries or looking at it and then manually constructing a model. We may overlook a lot of very good indicators of the health condition. We really do need AI to help us manage these problems. And because very often you hear people saying, okay, if AI is that problematic, maybe you should not be using AI at all. And it is a little bit like, because there are some problems, we just make life more difficult for everyone. And that's not a good solution. But, and this is something I fully agree with, they expressed hope that one of the things that comes out of the paper is that before something like that, a system like that hits the market, that there should be a basic set of audits before the product touches any real patients to check parity of predictions and things like that. If you do this kind of study and you find out that there is this disparity in predictions, and that black patients are underrepresented, white patients are overrepresented, there could be reasons for that. It does not necessarily mean that there is discrimination, but then you can check and either maybe find the reason why that is the case, or otherwise maybe retrain the algorithm to avoid this kind of problems. And there is a link to the paper. It's very readable. Also, if you're not into medical sciences, so I can absolutely recommend you to read the paper in more detail. Voila. So that's the first example. The second example, you probably have heard about this. Amazon that ditched AI recruiting tools that favored men for technical jobs. So this is 2015. Amazon claims they never used the algorithm, but that they disbanded the algorithm before starting to use it. because it was biased against women. And what does it mean, biased against women? And so the algorithm was based on a number of resume CVs that were submitted over the past 10 years. Most of the applicants were male, and so it was trained, or as a result of the training, it favored men over women, and even in a very cynical way. So it penalized resumes that included the word women's, like and the person was women's chess club captain, and downgraded graduates of 2 all-women colleges, for instance. And so this is quite severe, I would say. This is something that you do not want to have. So how does bias appear in CV screening? And if you want to use this kind of tools like language, natural language processing tools, this is something that you need to be aware of. And so most language processing transforms data first into numbers, because with numbers we can work easily, then we can train our neural network. But of course, first we need to translate our resume into numbers. These transformation methods, and they are widely available. We can download this kind of embeddings of words or transformers, like BERT, for instance, that turn text into numbers, and then we can train on those numbers. So word embeddings, however, these embeddings, word embeddings, I call them, or they are being called. So translating a text into a list of numbers. So we're embedding text into a multidimensional space, a point in multidimensional space. So we make a representation of words and text as a vector of numbers. For instance, we have banana, father, baby, and this is in 4 dimensions. Usually it's like higher dimensional, 300 dimensional, for instance. But here I made an example with 4 dimensions. And one thing that we want to have, and so these why do we do that? Because these embeddings, they are some kind of adapter, and some piece we can put in between, and then we can use all our algorithms in order to that work on numbers. One thing we want to have is that these embeddings are semantic. So we also want to capture a little bit the meaning of the words, because otherwise it would be easy and just make a vector that is as wide as the total number of words that exist in the language that you want to embed, like let's say 10,000 dimensional, and put a 1, every position corresponds to 1 word, like the 1-hot encoding, put a 1 in the position that corresponds to that word and a 0 otherwise. But instead of that, we want to have a lower dimensional representation that puts words that are semantically close, also close to each other. And so father and baby would be closer to one another than father to banana and baby to banana, and because the last 2 are people and the first one is food, and we eat bananas, but usually not fathers and babies. So words used in similar contexts should have similar vectors. Here is an example that illustrates this, where I did it manually, and we have positive and negative words, that's 1 dimension. We have words that you say, adjectives that we say about food, adjectives about people. And so, for instance, dense, obnoxious, this is something that we say about people, and it's rather negative. This is not something we say about food. So those 2 words end up in a similar position because they have the similar kind of negativity and a similar kind of way of do we use it for food or people. Delicious is very positive, but it's more common to use it for food than for people. Excellent, good, bad, and these are things that can be used for food and people, and that are positive on the one hand and negative on the other hand. So we want to do something like that, but we want to do it automatically. And so, and probably most of you are aware of this, and basically what is being done to train these, instead of having a label assigned, and like excellent has 2 labels, positive and neutral, when it comes to food or people, and now we're going to train and we will learn a model that works for every word. Instead of that, we're actually going to learn an AI for a different problem, and some kind of generic problem for which we can very easily find labels, and we turn the problem into a game. And the game is guess the word. For instance, here I have a sentence, 1 word is missing. Florida man charged for assault with a deadly weapon after throwing something into Wendy's drive-thru. And so basically the algorithm, based on the surrounding words, should be able to predict what word is missing. Does anyone have an idea what would be the word in this case? What would be thrown through the drive-through window? Sorry? Knife. A knife, an axe. Yeah. No, it was actually an alligator. Yeah, it's those Florida man type of sentences. So why is this such a cool idea? Because it's very easy to generate test data. Just take any text, take out a word, and then you have the label that needs to be predicted for that. Florida man charged for assault. Charge is missing, so we have the label for the problem over there. And so here I took 2 words before, 2 words after. We can take more words before, more words after, or we have different variants, but in principle it comes down to something like this. Then the structure of the model is fixed, and so there, and this is like really an essential part of these embeddings. So basically what they're trying to do is you have the different words, then we have a model that turns these words into what later on will be the embeddings, and then our algorithm should be able, and we should be able to learn a model. Wow, this is so cool. We should be able to learn a model that based on these embeddings can make our predictions. So our input will be given the different words that are given, and that will be just a normal one-hot encoding, as we call it. This basically means that if we have 2 words before, 2 words after, and we have 10,000 words in the English language, let's say, that this is 40,000 dimensional input, but only 4 will be 1, all the rest will be 0, and so there will be 4 vectors of 10,000 items that indicate the 2 words before and the 2 words after. This is turned into a representation by model 1. Basically, it means that we have a matrix there containing the embeddings. The embeddings are learned, and then based on the embeddings, a second model should be able to make the prediction what was the word that was missing. So here in this case, the output will again be 10,000 dimensional, but now we'll give the probability of the different words. And so it says we have 70% probability charged is the word that should be there in between Florida man and for assault. So now when training this model, there will be an objective that we want to maximize. And basically, we want to maximize the loss. And that's the one that is here. So for our given data, so we have the x, y. So these are the given problems in data. Have Florida man for assault is x here, and charged is y here. And basically, we want to optimize this loss. So basically, we want the prediction that the model is making will be equal to or will be as close to the right word after all. And so here in this case, charged is the correct solution. And so our y will be a vector with a 1 in the position of charged. And our loss function will be something that is optimized the closer we are to the right solution. But we do not tell the algorithm at all how it should make this embedding. This is just part of the problem. It can choose to have the first dimension to be the first letter of the word, the second dimension, the second letter, the third dimension, the third letter, or it can choose to have the fifth dimension, whether the number of letters is odd or even. We don't care. We do not force the algorithm in any way or another what should be there. We just hope that it will find out, because it's basically, this is a very narrow level, so it should be able to reconstruct and know which words are close to one another and based on this representation. It's a little bit like that you need to predict if 2 people are friends, but the only thing you can use are some characteristics of these people. And so basically, you need to predict if 2 people are friends. You're allowed to turn them into characteristics, and you can use 3 dimensions. And then another person, based on these 3 dimensions, should be able to tell if those 2 people are friends or not. If that is the case, you will try to make these 3 dimensions in such a way that they contain some semantic information, like maybe in what kind of sector do they work, what kind of hobbies do they have, and what age category are they in. This will be your 3 dimensions, and then based on that, another person can or cannot reliably predict whether the 2 people are friends or not. And here it's the same, and so based on the representation of the words, we need to be able to tell if which word should be in between those words. And this works remarkably well. And then after we have solved the problem, basically the representation of the words will become this narrow vector on the basis of which we need to decide what is the missing word. So if we look at those embeddings, they capture semantic information. That allows you to play the guessing game, but it also allows you to do a lot more than just the guessing game. It also allows you to learn whether a message is positive or negative, based on if a word is positive or negative. Based on those vectors, you can learn a classifier, and that based on those numbers predicts if it's a positive or a negative word, based on some given data. So here what you see is a projection of word2vec, and word2vec is one of those embeddings that captures this semantic information, and it's projected in 2 dimensions because for visualization. But what you can see is if you look at the differences between words in position, that this captures semantic information. So if you look at dark, darker, darkest, soft, softer, softest, yeah, that's here, clear, clearer, clearest. If you look at the differences between the words, then you see that they're more or less similar. So this means that the information, that these are comparatives, and the fact that slower and slow, the difference between slower and slow is they have the same meaning. Only one is the adjective, the other one is the comparative. This information is captured in some of the dimensions, and a combination of these 2 dimensions that have been mapped here. Short and shorter, if you look at the difference, so that kind of information is captured. Also, and this will become more important for us later on, also like gender information. Brother, sister, uncle, aunt, man, women, sir, madam. And these type, if you look at the differences, and this is also more or less the same. So this can be used, I will come to you in a minute. So this can be used also to solve this kind of riddles. Slow is to slower, like short is to, and then you can take short and then you add the difference between slower and slow, the difference between these 2 vectors, and you add that to short, and basically you'll find the position of the word shorter. And so in this way you can solve. It contains a lot of semantic information. Question? Yeah.
Do you also have kind of an explanation as to why the model learned to kind of have these properties of a, let's say, shorter and short difference being similar to slower and slow difference? Because in principle, the embeddings could be anything. So what's kind of the mechanism that has kind of guided them to be similar?
Yeah, so because this information is important for predicting what is the missing word. And here in this case, it's relatively easy to explain, I would say. And because if you have shorter or slower, it's very likely that the next word will be then. So if you need to predict what will be the next word, this is very important information if it's an adjective or the comparative.
It's an important piece of information, but I mean, important information could also be represented some other way, perhaps. Is it kind of, if you have this property, then it is the easiest to kind of linearly extract that information from the embedding, or how else to think about and why?
I think it's more like some kind of post hoc thing. So if you train this kind of embeddings, what you see is that in some of the dimensions or in combinations of dimensions will contain the information that allows you to derive this kind of information. Also, the gender of words is another thing. If you train using this type of training problem, the embeddings will allow you to distinguish the gender of the words. This is more like something that has been observed, but I can imagine, because it's just an optimization problem, that it will find another way. But it turns out that for all of the embeddings that are available there, that this type of information is always there.
Is it also true for the newest LLMs?
Yes, yes, yeah. So here, because this, and this is maybe also a small extension that I need to talk about. And so what I have explained here is what are so-called non-contextualized embeddings. And so this means that a word, independent of the context that it is used in, will get exactly the same, assigned to the same vector. If you look at more modern techniques, they also take into account the context of the word. Like if you take stick, the word stick, stick to the plan, or the man hit the dog with a stick, and these are two different sticks. Then in the non-contextualized embeddings, this type of embeddings, they will have the same vector. In contextualized embeddings, the more modern variants, the birds, for instance, and the GPTs, they will also take the context into account, and they will create different embeddings. But the idea is the same. They're also trained on some generic problems. If you look at BERT, it also has this mask language model on which it is trained. And like you mask some of the words, and then you need to predict what are the missing words. And also another task is to see, take two sentences, are these two sentences a logical consequence, or is it logical that these two sentences are next to each other in a text? And so this is also data that you can easily generate. You take any two sentences in a text that are next to each other, and then you just take two random sentences and you put them together. In the first case, you have a positive label. In the other case, a negative label. So also some generic tasks on which it is trained in order to learn a representation which allows you to solve some generic problem. And this representation contains a lot of semantic information. This has some amazing applications. I would say nowadays, if you're doing NLP and you're doing some classification problems, most likely you're using this kind of techniques. So for instance, sentiment analysis, predicting whether a word is positive or negative. And so we can first train our embedding, and people have done this and have made them available, and they are trained like Word2Vec. You can just download it. There are Python packages that will do this for you. You can just apply them to a text, two words, and then you have a vector representation of each word, and then you can predict whether a word is positive or negative. So what is cool about this is that if you have, for instance, you know that the word good, the word positive, that these are positive words, but then there is another word that has not been seen during training, I don't know, elegant. Then because of the position of elegant, it can derive that this is probably a positive word, and because of the semantic information that is captured. And so we can use it for sentiment analysis, like one of the professors at the University of Antwerp is using this kind of techniques and to automatically detect cyberbullying on social networks. And this works much better than the techniques that are based just on the words that are present in a text. But, and this is of course the backside of the medal, it also captures cultural biases. So for instance, and this is an example from the paper from Boluk-Basi and others, if you have these analogies and you ask man is to women like computer programmer is to, and then the system based on this type of embeddings will answer homemaker in their study. This is if you want to make predictions, you want to predict what word is missing in a text, and you want to do it in similar texts as those that were used for training, it probably makes sense to have an embedding that assigns the words more like that. But of course, if you're then going to use this in for screening CVs. To find the perfect job for you, you need to be aware of these biases that are present in the words there. These gender stereotypes have some she-he analogies. Sewing and carpentry are two versions. As carpentry is considered the male version of sewing. A surgeon is considered the male version of a nurse, and so on. And so you see a lot of the cultural biases or the job stereotypes coming back there. This is a problem. It's already 2016, so 7 years ago, that it was remarked. People have been working on this. Have been trying to, also the paper of Boluk-Basi is one of the first papers that tries to address this, but still these problems keep emerging to some extent because of the generic problems that are used for training the models. Some examples, so this is for Word2Vec, also ethnical information. So here what I did is I took the similarity between popular ethnic names and terms. I used data from the United States. There you have lists of the 10 most popular black names, male names, the 10 most popular names for black females, for whites, and so on. And then we just took the cosine similarity between the vectors of different words and the or the average distance of the names to the vector of those words. And then you also see a clear stereotypical image emerging. For instance, robbery, which is more connected to the black male names, because of the system probably be trained on news articles that are heavily biased towards, etc., etc. There are explanations, but if you're going to use this in another application for jobs, for instance, it means that male black names will have negative connotations with them that are carried over to the representation. Also things like words like intelligent, trustworthy, professional, and there you see that these are words that are more likely to be associated with males than with females according to the embeddings, and they're closer to males than to females. It's very hard to remove these stereotypes, as people have been working very hard to remove them, both directly from the models and also building something around those models. And for those who have been using ChatGPT, and probably everyone in this room, you notice, you feel this, that there are some questions that are being blocked, everything that is like kind of racist or reinforcing some gender stereotypes. It's always answering very neutral. But even there, if you ask, for instance, a prompt, a carpenter and a teacher get married, she asks him to make, here in the sentence, a carpenter, a teacher. These are both neutral, so basically you don't know which of the two is the male or the female. But you will see that the system basically assumes that the teacher is a female and the carpenter is the male, which is probably fine if you want to predict which word is missing or what is the most likely continuation of the text. But if you use this as the basis to screen CVs and to make predictions who is more or less suitable for a job, these are things that you should be aware of, and that they may introduce some bias in your system that you need to capture before it goes to the market. And so in the case of the male that needs to make something, then it's a bookshelf, and the female that needs to make something, it's a lesson plan for his carpentry students. Voila. So this is the second example. Then the third example, this is about the COMPASS system in the United States. And this will also already be a jump towards the next topic, where we will be discussing different fairness measures. Because this is really a very well-known example, but where people stop explaining too early, in my opinion, because there are different ways to look at this, and depending on from which perspective you look at it, it's either an incredibly discriminating system, or maybe it is fine after all. So COMPASS stands for Correctional Offender Management Profile for Alternative Sanctions. And basically, it's a system to predict risk of recidivism. So you have someone who convicted, and then basically you want to predict whether or not this person will commit a crime again. So the label is, was there a new arrest within 2 years after the person being convicted? Data on which it was based were pending charges, prior arrest history, previous pre-trial failure. And so if you do not show up in court when your trial is on, that's a pre-trial failure. Residential stability, substance abuse, also family situation. Is there someone with a criminal background in the family? The neighborhood, the environment of a person. Lots of those data elements were there. And ProPublica looked at this system that was used in the United States, and judges were even using it in their rulings. And some were saying like, okay, I will not this patient cannot bail because of the risk score that he or she is getting. And so ProPublica did a study, and this study showed that the errors that were made by the model to predict recidivism were highly biased. What does it mean, highly biased? And so we look at people that are labeled higher risk but that did not reoffend. And so it's an error. So they were labeled as high risk, but they are actually not recommitting crimes, or they're labeled as low risk and were recommitting crime. And so you see for white Americans, and for the first type of error, there is a much lower probability that this error will be made, and so they will be labeled high risk while they're actually nice people, let's say. And for African Americans, and the risk was much higher. So how to interpret the numbers, because I find the table a little bit hard to interpret sometimes. That is 44.9, means that 44.9% of the African Americans that do not reoffend were misclassified as high risk. And so for the white people that did not reoffend, at 23.5 were assigned. And for the other way around, the labeled low risk, but you did reoffend, so it's positive for the criminal, let's say. They get a more positive label than they deserve. There you see that the error is much more likely to be made for the white people than for the African Americans. Of course, in a heavily polarized country like the United States, and this is dynamite, and this causes a lot of distrust in this system. And many people stop explaining this case here. However, I think it's also important to look at the claim made by the developers of the system. And so NorthPoint is the company that made the system, and they're actually claiming, no, the scores are fair, even though all the errors that you're seeing, the scores are fair because they're calibrated. So what does it mean that they are calibrated? So if you would look at the labels that people get assigned, you get low risk or high risk assigned. And then you look at, in the low risk class, people that got assigned the label low risk, how many of those recommit a crime? So that's the recidivism risk. And for those in the high risk class, how many recommit a crime? Then you see that in both of these subgroups, it's more or less the same, which is a good thing, because it means that if you say someone is low risk, you can interpret what it means without knowing the ethnicity of a person. Low risk means, let's say that it's 30%. And so here, the system is not perfect, so for those for whom I'm predicting low risk, still a fraction will recommit crime. I do not need to know the ethnicity of a person, it's the same. 30% if you're low risk. High risk, 80%. It doesn't matter what is your ethnicity. That's a positive thing, that's good to have. I would even say it's necessary to have. Otherwise, the judge would have to look at the ethnicity of a person and would have to say, it's low risk, oh, but it is black low risk or white low risk, and there is a different interpretation. No, there is not. There is no difference between that. Then how could it be that there are so big differences if you look at the errors that are being made? Well, let's analyze what happens in this case. So let's see where are the false positives and the false negatives happening. And so where are the people that are predicted to be high risk but are actually low risk? And where are the people that are predicted to be low risk but are actually high risk? If you look at this, and so where are the people that are predicted to be low risk but are actually high risk? Where can I see how many of those there are? in my graph? Somewhere in between is being said. Do you all agree? Or? And so these are the labels. Oh, I need to point here. Oh, what happened? I managed to break it. So on the left bars are those people that are actually are predicted to be low risk, and then the height of the bar indicates how many of those are actually high risk.
You don't show how many there are in each.
Exactly, that will turn out to be the case. So everyone who is a false negative, and so who gets the beneficial label while they actually deserve the high risk label, they are in green. They're all in that left group, all those errors. All the ones that are false positives, and so they turn out to be recommitting crimes, but they are actually labeled with the low risk or in the red part. And so it's 80% was the height of the bar I told you. So it means there is still 20% that's in the high risk category and that did not recommit crime. It's logical, eh? Those systems cannot be perfect, so errors will be made. And black is in this data set, or in the data set of ProPublica at least, relatively more frequent in the high than in the low risk category. In the ProPublica case, there are actually also a medium category, but here I just took 2. So the relative participation of black in both groups is higher in the high risk group, where all the negative errors are being made, and they're underrepresented in the low risk category group, where all the beneficial errors are being made. Voilà. So to summarize this point, we have the whole population. They get assigned a score, high risk, low risk, by the COMPASS algorithm. Some of them recommit crimes, some of them don't. So then ProPublica does the analysis. So basically they divide people into different groups, and those who do not commit crimes, did not recommit crimes, and then they look at the predictions that are being made for the black people and the white people, and those who did recommit crimes, and then divide it according to the ethnicity. Then they look at the numbers of those who are in the category of not committing crimes. 1/3 of the blacks actually got the negative decision, and 1/5 only of the white people. And then on the other side, you see the same. So basically, ProPublica is saying, okay, in order to be fair, these numbers should be the same, and these numbers should be the same. If we now look at the North Point analysis, they just divide them in a different way. They just look at those people that got assigned the positive label, those people that got assigned the negative label, and then you see that the two fractions are the same. It's a bit counterintuitive, and there is also a very nice tool online. I will share the link with you. I don't know if it's on in the slide, where you can, with a slider, decide yourself who will be in which category, and where you basically see that there is no perfect solution. You cannot have both of them at the same time. Voila, and so that's for this case. So is there discrimination or not? Actually, it's hard to tell. It depends on your perspective. Now, for this case, I would say, if you look at in total how many errors that are being made, there is, like here, if you accumulate all those numbers, it's only correct in like about 60–70% of the cases. Maybe we should not be using a system that is this inaccurate in order to make this type of very important decisions after all. Voila. Comments, remarks? Just maybe a poll. I'll come to you in a minute. Who thinks that in the last case there was discrimination? Okay. Who thinks there wasn't? by 2-1. There was a question over there.
So I want to maybe ask a bit higher question about fairness versus privacy. So for example, in the last case, if you had, for example, more data, for example, very specific data about each person, like who they go around with, if they go around with criminals, what do they do every day. If we had very detailed data about person, we could make more accurate predictions. So we could remove bias because we know very specifically what the person needs, that we have a very, very specific characteristics about the person. But that would again invade privacy because we don't actually want to give government information about what we're doing every day, who we go out with. So how do you see how to balance this equation? Like, should we collect more information about people, invade their privacy to make more fair predictions about various things? Or should we limit ourselves to more general prediction, let's say variables like race and things that most of the time, let's say, works. Let's say black people maybe are more criminal. That works some of the time, but if you make these very, let's say, vague predictions, we will introduce bias. So, but again, then we won't even invade privacy because we don't collect more people about specific individuals. So how would you comment on this dichotomy?
Mm-hmm. Yeah, there is definitely a tension between the two. Let's maybe take the insurance example as maybe a somewhat less loaded example to illustrate this point, where we had the risk between males and females, where males are doing more car accidents than females, not because they are male, but because of a lot of characteristics, maybe more risky driving behavior that may be associated with, I don't know, may have more testosterone, I don't know. If we would collect more data, like we would, the insurance company could collect data from our cell phone, where we were, how fast we were driving, how fast we were taking, cutting corners and things like that, then they probably could make a more reliable estimation of the risk of risky driving behavior. And they would not need the gender of a person anymore to make this prediction. So there is this tension between privacy and discrimination. Because of having more information, we will have less discrimination in our models because there are other ways to assess this information. It's like, luckily, I don't have to make this trade-off. And like if you look at privacy regulations, there are a lot of European regulations, for instance, where they look at a number of aspects. And one of those, and maybe that's the one that's important for your question, is that of proportionality. Basically, they're saying that you can use information about a person, or you can collect information about people if it is, which is private information, if it is well justified and proportional. And by proportional, they mean that it's not possible to gather the same information in a less intrusive way and to build an equally good prediction model in a less intrusive way. That's one aspect. Another aspect is, okay, the goal should be proportional to what you want to do. So if it is in order to make advertisement, then it's probably not proportional to invite people's privacy. But maybe when it comes to criminal activities, it could be decided by data protection agency that it is proportional to do that. Yeah. But this is a trade-off that we need to make. This is something, I would say, which is not the data scientist that needs to make it, but there are other qualified people that need to make this trade-off. I know it's not a black and white answer, it's kind of a gray zone, but I think it really is the case. It highly depends on the situation, whether it's proportional to collect and use this data or not.
Thank you.
Right. All right, so let's then continue to fairness measures. And so we have already seen 3 cases where there were some issues. You could, depending on how you look at it, it's more or less of an issue. And so basically the goal of fairness measures is we want to have a way that based on some data and the model that we have, we can decide whether a red flag needs to be raised and whether there might be a problem or not. So I'll now go through some of the most common fairness measures. If you're reading the fairness literature, and you will come along those measures. A first category of measures will be group fairness measures. After the group fairness measures, I would say something about trade-offs and impossibility results, and then maybe something about individual fairness, depending on the time that is left at that point. But so group fairness measures, and so these are statistical measures, so we look at the whole population, and we want to see by measuring errors that are being made or predictions that are being made on the whole population, whether there is discrimination or unfairness or bias or whatever you would like to call it, and if there is a reason to inspect more closely what is happening with our classifier or with our model. So ProPublica studies and Northpoint's response, they are both fairness measures, group fairness measures, because they look at the whole population and they compute statistics of the whole population. Later on, when we talk about individual fairness measures, and then we are going to look at a decision has been taken for an individual person. Is this one person being discriminated? Did he or she get the wrong label by our classifier because of the ethnicity of that person? And if that specific person would have been white instead of black, would have been male instead of female, would the label have been the same? That's an individual fairness measure. Here we look at the group fairness measures. So how do we define whether the decision procedure is fair? Already ProPublica study shows you that it may depend on your perspective. So here are the two. So a first attempt that we could try, and this is the first thing that everyone will try, is, okay, if we do not want to discriminate based on gender, ethnicity, etc., just leave out those attributes from your data and the problem will be solved. However, and this was already realized many years ago, this does not work. We can still build models that are based on correlated attributes. There is the example, this was called the redlining effect. And the redlining effect, this comes from the fact of redlining, where banks, it was in the United States again, when they were no longer allowed to use ethnicity of a person in order to allow or disallow loans to those people, and they started actually coloring in regions on the map, and people that were living in certain areas were disallowed automatically their loans, not because of their ethnicity, but because of living in that area, and so according to the law, they were not discriminating, and they were using red lines to encircle this kind of areas, and hence the redlining effect. Of course, not surprising that those areas that were disallowed loans had a lot higher a percentage of black people living there than the areas where the loan was allowed. So that's the redlining effect, and our algorithm will do the same. If there is signal in these sensitive attributes and they're correlated with other attributes, these other attributes will be used to pick it up. If you look at the CV of a person, you remove gender, the name of the person, looking at the hobbies, the schools they went to, lots and lots of other triggers are there, and that allow you to predict accurately the gender or ethnicity of a person. So here is a simulation we did. And so this is a simulation where we use the adult data set, which is available in the UCI repository. This data set basically contains information about people and their income. And we made some kind of simulation, and we said, okay, now suppose that a bank would use this data set in order to predict whether someone has a high income or a low income, and based on that, they will assign a loan or not a loan. If you look at the data, this is in the original data set, then we see, it's probably hard to tell directly from the numbers, but there are more males with a high income in the data set than females. So, and for those who would give a loan or no loan, we would give more loans to males than to females. If you look at the difference in probability that a male has a high income and the probability that a female has a high income, it's 19%. So there's a 19% difference. So now we learn a classifier based on this data in order to make predictions. So this is on a different set, a test set, an independent test set. If we then look at the difference in probability that a male gets the loan or a female gets the loan, it increases to 31%. And it can be slightly different depending on which model that you're using. I think this is a random forest model that we used, but it's actually quite common that this percentage is increasing. And the reason for that is that because our classifiers are based on the information that is in the data set, but there are hundreds of reasons why someone has a higher income or a lower income, and our algorithm can base itself only on those characteristics which are in the data set. So it will overemphasize on those, which will mostly result in this type of bigger differences. Let's take our insurance example. Suppose that we only know if a person is male or female. That's the only characteristic we have. And males have 60% incidence, females have 40% incidence with the car. Then we will predict males as being high risk if we want to learn the most accurate model. And we will assign 100% of the males the high risk and 0% of the females the low risk. And so where the difference was 20%, now it becomes 100%. Something similar happens here because there are many reasons, but only some reasons are known. So we're overemphasizing on those reasons. Voilà, that's why the difference is increasing. If we now look at predictions that are not based on gender, so we just removed gender from the data set, it got a little bit lower, but it's still 28%. And that is because a lot of the other attributes contain information that correlates with the gender of a person. And this is true in like almost all data sets. If we look at sensitive information, we remove those attributes, and they're usually derivable from those other attributes. Another example is, for instance, ethnicity of a person. If you look at the first name, the last name of a person, and the place, the postal code where the person is living, then you can make a relatively accurate prediction of the ethnicity of a person. That is something that is used quite often in order to derive or to add a label ethnicity in datasets where this label is unavailable. If people want to do in sociological studies, if they want to see if there is some difference between different people from different ethnicities in acceptance rates for jobs or tax fraud or criminality or whatever, and this information is not available. So a lot of other attributes contain that information. So that doesn't really work, so there is no quick fix. So we need some statistical measures and the group fairness measures. We will look at 3 of those: statistical parity, equal odds, and calibration. So statistical parity, this just means that we have 2 sensitive groups, and I will use the normal naming way in the literature. A is the sensitive attribute. A is 0 means one group, A is 1 is the other group. A0 is usually used for the group that needs to be protected, in our opinion. A equals 1 to the reference group, the other people. We have true labels, and then we have predicted labels. And so we use the normal convention. Y is the true label, Y hat is the predicted label. In an ideal situation, Y hat would always be equal to Y, which means that for everyone we make the right prediction. In reality, that will, of course, never be the case, or seldomly be the case. Statistical parity means that we want both groups to have equal access to the benefit. So the probability of Y hat equal to 1 given A is 0 needs to be equal to the probability of Y hat equal to 1 given A is 1. So our insurance example, Y is 1 means that you get a beneficial insurance premium, a low insurance premium. Y equal to 0 means you get an expensive insurance premium. A equal to 0, you're male. A equal to 1, you're female. So we look at so the model that is used by the insurance company, which percentage of males gets the cheap loan insurance, and which percentage of females gets it. And then we look at the difference between the two. And we want this difference to be low or to be equal. So usually when we measure it, we will look at the difference between the two, the absolute value of that difference, and we want it to be 0. And then typically algorithms would optimize accuracy constrained by statistical parity. So for instance, acceptance rates at the university, suppose we have males, females, some are accepted, some are declined in University A, University B, then University A will does not satisfy statistical parity because there is a big difference between accepted males and females. There is 11% difference between the two, and in University B, there is not a difference. Before you start protesting, there are pros and cons. Pro of the statistical parity, it's like affirmative action. So we offer CEO jobs in equal proportion for all genders, even if that was not the case in the past. That is basically what we do in statistical parity. Our data set may tell us otherwise. The model that we learn may do otherwise, but we want basically to constrain a model that it satisfies this affirmative action. So learn the best assignment. We want to hire professors, males, females, but we want to hire them 50-50 proportion. And our algorithm needs to be as accurate as possible with respect to the historical data we have. Who did we hire in the past? But now it needs to be equal. But then an obvious weak spot is, what if there are explainable differences between the groups? For instance, diploma held by the candidate. If you have 1,000 male candidates for a computer science job and 10 female candidates, well, then no one would think it's reasonable to have an equal proportion. And this is so we need to condition. And so conditional statistical parity is basically what is used there. So we add another variable, a condition C, that explains part of the differences. And so then basically, and for all possible conditions, we want to have statistical parity. So basically, we want to have statistical parity if we only look at those people with CS diplomas, and we want to have statistical parity if we only look at those people who do not have CS diplomas, right? So acceptance rates at the university, and there we had University A that was discriminating according to our statistical parity, University B that was not. However, if we would split up according to the departments or the faculties for which they are applying, and then it turns out, for instance, here in University A, that the difference comes from the fact that females are more likely to apply for those faculties where the acceptance rates are lower, and then we will not consider this discrimination, or not necessarily consider this as discrimination, because we can explain it by our condition C. And so here in this case, if we turn it into probabilities, then we see that even though University A overall has differences within the faculty, it is the same. Or University B looks like having not a discrimination problem, but within the faculties. So probably there is something artificially going on here. And then here in this case, we would basically say that in the first case it's satisfied. In the second case, it is not. To already counter question that may come from over there, what is the condition that we need to set? What is an acceptable condition? Which condition should we consider? This is again something that, in my opinion, the computer scientist or the data scientist should not be deciding about, but like an ethical committee should basically be looking at. And then we can basically do this conditional statistical parity. A well-known critique of conditional statistical parity is that it is hard to fully identify all acceptable explanations of differences. If it wasn't, then we wouldn't have to be relying on machine learning, right? If it was easy to tell which characteristics are acceptable to distinguish people and which ones are not acceptable, then we would not need machine learning to learn which characteristics determine the label. We could just use those. Yet there might be differences between groups. Also, some attributes may be like partially acceptable and partially not acceptable. Suppose that you want to give a loan to someone, and you want to decide, should I give a loan to a person who is applying for a loan for a house? Then the neighborhood is associated with the ethnicity of the person. So you do not want to see a system where consistently in black neighborhoods you're not giving loans and in white neighborhoods you are giving loans. But on the other hand, the average prices of houses in the neighborhood will affect your decision. And what is the loan amount? What is the average price? If the average price in that neighborhood is much higher than the average price in that neighborhood, it's probably not a good idea to give the loan, or it could be a reason not to give a loan, and that could be acceptable. So you cannot say postal code can be used or cannot be used as a factor here. So therefore, basically what we can do is we can look at the errors. So instead of dividing the people according to some characteristics we think are acceptable, we will divide the people according to the label they have in reality. So we'll look at, for those students that are successful, how many of those get accepted if they're male and female, and those students that are not successful in their studies. These are our two groups that we will be using, and this will be our attribute C. We will use our label actually as our attribute C. And then we get the equal odds measure. So errors are acceptable, but should be similar for all sensitive groups. So that is basically what we want to have, what ProPublica wants to have. If we look at the errors, and those that are labeled high risk but did not reoffend, then for whites and African Americans, they should be the same. Low risk but did reoffend, and those percentages should be the same. This is actually very similar to our conditional statistical parity, where our condition is just the true label of the person. And so we have divided the people into two groups: those who deserve the positive label because they didn't reoffend, those who do not deserve the positive label because they did reoffend. And then in the first group, we want the probability that you get a positive label to be the same. So the labeled high risk should be the same. It's not the case here. And in the other group, we also want this percentage to be the same. Voila. So here, translated in other words, so the equal odds basically says, in the ProPublica case, if you deserve to stay in prison, it shouldn't matter whether you're black or white for your outcome. If you deserve to be released, it shouldn't matter whether you're black and white or white with respect to the outcome. And so that is that formula. So this is the second measure, and so statistical parity, the conditional statistical parity, and equal odds like an extreme case of the statistical parity. The next one is calibration. And this is basically what we were talking about, where North Point used to defend themselves. So calibration is a concept from classification. And it basically says that the probabilities that a classifier is giving, that they should be calibrated, they should reflect reality. And so the probability that, and so this is basically used in the case that your classifier is giving a score. And the probability that you, in reality, someone has a positive label and should be equal to P if the predicted score is P. It's like, so the weather forecast and the weatherman or weatherwoman predicts that it will rain with 20% probability. And so basically you lump together all the days with 20% of rain probability. And if you look at all those days over a whole year, and then 20% of those days it should be raining. Voila. And then that's calibrated. And so if the prediction is 20%, then if you lump those together, it should indeed be 20%. Any classifier you can make calibrated by estimating the class probabilities. You can just look at the probability. So your prediction for the score is equal to the probability that the true label is 1. And so basically you look at, and suppose you have a classifier, and a classifier says, okay, you're in the high risk group or in the low risk group. Then on our test data, we can see for those who are predicted, or on a validation set, we can look at what is the percentage, how many errors are we making. In the high risk group, if 80% in our validation set gets the positive label, then our score will be 80%. In the low risk category, it's 20%, so then our score will be 20% for the low risk category. This can be extended to multiple labels, and basically what we want to have with calibration, if we look at different sensitive groups, and then calibration basically becomes that we want to have this thing here. If we look at those who get the positive label, and those who are in the one sensitive group, and those who get the positive label and are in the other sensitive group, and the probability of having the positive label should be the same. And that's what we call calibrated. And so basically it means, and like here, we have our 3 outcomes, low, medium, and high in our ProPublica case, that black and white should have the same proportion. And for medium and for low, it should be the same. And then we call a classifier calibrated with respect to the ethnicity in this particular case. Voila. So many different measures. So in a real application, suppose you're building a model, which one should be satisfied then? Maybe all of them. And so there kicks in trade-offs and impossibility results, which basically tell you that it's impossible to satisfy all of these measures at the same time. So let's look at an easy case at first. Statistical parity and equal odds. So statistical parity, and that's this affirmative action. We want that males and females have the same probability of being hired as a CEO. We want that blacks and whites have the same probability of being seen as a high risk. That is statistical parity. Equal odds is we look at the errors that are being made. So if we look at those who are misclassified, then we want that the false positive rate and the false negative rate, that they are the same for both communities. Both of them make sense in some context. But let's look at an example. Assume that males are higher risk than females with respect to car insurance. This example keeps reoccurring. And we want to assign expensive premium to high risk and cheap premium to low risk clients. At the same time, we want to be fair with respect to gender. And suppose that we want at the same time equal odds and statistical parity. So there I've written demographic parity. These are 2 terms that are used interchangeably, demographic parity, statistical parity. So suppose that we have this distribution of risk. So for males, 40% has a high risk behavior, females 20%. This is what we observe from data. So these are the true labels. And so these are every of the 40 there and the 20 there is associated with a car that has crashed, and costs that have been paid by the insurance company. Equal odds then basically says that premiums should depend on the actual risk and not on gender. Makes sense. And we suppose that we consider 2 premiums, cheap versus expensive. Demographic parity, we want the same number of males and females with cheap insurance. Clearly here already you see the tension, and this is like a kind of warming up case. So equal odds and basically means if you look at males and females and we look at the risk category, low, high, that we want to have the same percentages there. And so here you see, and so 80% gets assigned to the low risk for the males, 80% of the females, and 30 for the high risk get assigned to the low risk. And so this is the percentage receiving cheap premium. And so this means there is 20% of the males that are low risk, but that they receive the high premium, because only 80%, but for the females it's the same. And for those who are high risk, still 30% gets the low premium, but for the females it's the same. It's a reasonable classification. Number of males and females having cheap premium here in this particular case, if that would be the statistics, then we would have there are 60 males that are in the low risk, 80% gets the positive cheap insurance premium, and there are 40 that are in high risk, but still 30%, so we get in total 60, they'll get the cheap premium. For the females, 70, so there is not statistical parity satisfied because there are differences here. Is it clear for everyone? So if we can make them equal by just giving every man, which is in the low risk category, the cheap loan, and 75% of the females, which is in the low risk category, the cheap premium, then there will be 60-60, because we have all those 60 and 60 of those 80 get the low premium, but then equal odds is not satisfied. And then if you replace this by letters and just do mathematics, then it very quickly comes out that this is only possible to give them to satisfy equal odds and statistical parity if A is equal to B, which basically means that you just toss a coin and that you don't care whether someone is really low or high risk. Because if someone is low risk, the probability is A. If someone is high risk, the probability of getting the cheap premium is A. That's not a good solution, and that we call a degenerate solution. So here in this example, it has been showed that there are cases where statistical parity and equal odds cannot be satisfied at the same time. So an intermediate conclusion of that: assume that we have sensitive groups that behave differently with respect to the target. Then enforcing demographic parity, statistical parity, means that you will make errors at different rates for both groups, because you cannot have both at the same time. And that the predicted label will not be independent of the group given the true label. And so this also kind of makes sense. If one group has a higher probability of getting a positive label than the other group, and in your predictions you want to make that equal, it will mean that you will have to make different types of errors, and you will have to make errors in order to get them equal in your prediction. Hence, it also implicitly assumes one of the following: that you're assuming, if you have statistical parity, that you're assuming that the labels in the training set are incorrect. Because otherwise you cannot justify to make errors at different rates, and basically the errors that you're observing on your training set, you assume that they're actually not errors, not always errors in reality, and because you're enforcing demographic parity. Or your labels may not represent your true target. In the case or very first example, does someone need a lot of care in future or not? There we could enforce demographic parity because we believe that the label may be tainted and the label may be biased towards one of the groups. And in that way, it makes sense to enforce demographic parity. Or that could also be the case, statistical parity could be a hard legal constraint. You have to satisfy, otherwise it is illegal. And this is what is happening in some cases when you're hiring people in order to have diversity, that there are hard legal constraints or constraints imposed by the university in order to have that. Voila. So I will not start on the next point. And so on Wednesday, we will continue because time is running out. But what I will show then will be that there are also this type of impossibility results when you look at equal odds and calibration. So this is the ProPublica case. And so also there we will see that it's impossible to marry these two constraints at the same time. So we will have to choose between those constraints. The fairness accuracy trade-off will be another point that is addressing your very first question, I think, where we will also look at that. And when the training set contains errors, then sometimes it makes sense to enforce some of the fairness measures. After that, next time we will look at fairness audits. So how can we check this in reality? Fairness intervention. Can we make algorithms that are fair by design? And then some outlook. All right, there is still a little bit of time left for questions, I think.
To be fair, everybody's waiting for lunch, right?
Yeah, I can also take them during lunch or coffee breaks. But okay, maybe someone over there.
So the last part of the lecture, we were discussing how can we measure fairness within our machine learning models. But there is some counter actions that we can take from the beginning that to make the system by design fair or not, and how practical is this idea?
So some countermeasures that we can take, I would say, like for instance, in the first case that I discussed with the health insurance. So there, one of the fairness measures could be used, and then you would find out there is a discrepancy in the predictions. Because of that, you probably find out that the labeling is wrong, and then a fix that you could do is in order to find a better label. So there, in that case, I would say it definitely makes sense to find a better label and to do something which actually comes before learning. I don't know if that exactly answers your question, but other checks you could do is, for instance, also check if you look at your target population and your training data that you have, do they follow a similar distribution? If that is not the case, maybe you should take some counter actions. This is, of course, not rocket science. This is something which is true in machine learning in general, but definitely in this case, in case of fairness and bias, it also makes sense because of legal restrictions that there may be.
Also, from the previous example that we concluded that in order to have like a fair machine learning models for the insurance example, we need to completely ignore whether the customer is a low or high risk. Does this mean it is actually impossible to filter out the gender, whether the customer is male or female, and take them away without altering or impacting the possibility to be like higher or lower risk customer?
Yeah, so it basically means that like if the two groups in your training data have different base rates, and so different rates of having a positive label, that there is no way to make it equal without making different types of errors in the two groups. So that you should accept that fact that you will make a different, that's a logical consequence of this difference, unless you want to give them A needs to be equal to B, which basically means that you're not trying to make any prediction at all, that you will just give the same, with the same probability, a cheap insurance to both groups, which actually also, yeah, and with the same error rate than in both groups.
Yes, thank you.
Okay, off we go for lunch. Thank you.